Balancing oxidation-reduction reactions might be trivial, but they can get pretty hairy. So what we're going to look at is we're going to look at a method for balancing oxidation-reduction reactions in solution. Almost all of them are done in solution. That will work as you go through them. There are a lot of aspects of balancing redox reactions that we just haven't come across yet. For example, let's say that you were given this redox reaction. Let me get it up here. All right, this is a redox reaction, and we could assign oxidation numbers and figure out who's oxidized and who's reduced, but we don't need to do that. If we were to balance this, you would quickly run into problems balancing it in terms of going back and forth using the methods that we learned before, simply because you're never going to be able to get the oxygens balanced. In order to get the oxygens balanced, you have to change the number of manganeses and so on. And so this is not a trivial go back and forth until you get all the atoms on the left and the right to be equal, because this is taking place in an aqueous solution, and that aqueous solution may be either acidic or basic. If that aqueous solution is acidic, then we have hydrogen ions, we have H pluses floating around in our water, and we have water floating around that actually may be participating in this redox reaction. Even though they're participating, they may not be written in sort of the skeleton of the redox reaction. And so what we want is we want a way to balance this redox reaction that allows us to take into account that there may be some H pluses or some waters that are participating. In the first step of balancing this, we need to split it into the half reactions. This is usually pretty easy. Essentially what you're doing is you're looking for elements besides oxygen or hydrogen. And for example, I see chlorines on both sides and I see manganeses on both sides, so there are my two half reactions. One of them looks like this and the other looks like this. Alright, now as written, again, neither half reaction is balanced yet, but we'll be going through a series of steps to balance each half reaction, and then we'll put the half reactions back together. The next thing, after splitting it up into the half reactions, is we're going to balance all of the elements except hydrogen and oxygen. The reason why we don't worry about hydrogens and oxygens at this step is because of what we talked about above. In an acidic solution, there are hydrogen ions, H pluses and waters, that are present and participating, and so we'll add them in a later step. So for example, I want to balance the manganeses. They are. I want to balance the chlorines. They're not. I need a 2 out here to balance the chlorines on this right-hand half reaction. For the next step, what we're going to do is we're going to balance the oxygens, and we do this by adding water. Now again, water is present. These are aqueous solutions, and so water contains oxygen molecules that may be participating. Now I don't have any oxygens in my right half reaction, but I do have oxygens in my left half reaction, so I'm going to need to add water. Notice that I have 4 oxygens on the left, 2 on the right, so it's going to take 2 H2Os to give me the 2 oxygens that I need on the right to balance the 4 oxygens on the left. So that's my next step. Then next, what we're going to do is we're going to balance our hydrogens by adding H pluses. We do this because in an acidic solution we will have H pluses present. If it's not an acidic solution, if it's a basic solution instead, then we will still do these steps, but then we'll have to add some steps on to the end. So let's worry about acidic right now. We'll do basic later. So balance the hydrogens by adding H pluses. Again, I don't have any hydrogens in the right half reaction, but I do now have hydrogens here because I added water. Do you see the 4 hydrogens on the right? Which means I need to add 4 hydrogens, 4 H pluses on the left. Be very careful about writing these charges. If you accidentally leave some charges off because you're going quick or you're being sloppy about it, it will give you the wrong answer in the long run. So these are 4 H's with plus charges that I added to the left. The next step is to balance the charge on each side of the arrow by adding electrons. Remember that these are redox reactions, and as such, they are transferring. There's a transfer of electrons. One of the half reactions will produce electrons, so the electrons will be on the right-hand side of the arrow. The other half reaction uses electrons or gains electrons, and so the electrons will be on the left-hand side of the arrow. Now, I don't have to know what it is ahead of time going into this. The charges guide me to decide where to put the electrons. Here's how that works. I'm going to get a little space first, and then we'll go. All right, as I look at the left-hand side, let's start here. I have 4 positive charges and 1 negative charge, so altogether on the left-hand side I have a positive 3. On the right-hand side, my charge is a 0. Nothing has a charge. What I'll do is I'll go to the more positive side and add negative electrons to bring the two charges to equal each other. I will add the electrons to the more positive side. This is a +3, this is a 0, so if I add 3 electrons to the left, that will balance the charge, because that would be subtracting 3 from the charge, so now both sides equal 0. Now they don't both have to equal 0, but they do in this case. If I look at my right half reaction, on the left I have a -2, 2 negative chlorines. On the right I have a 0. I want to go to the more positive side, that's the right-hand side in this case, and add electrons to make the charges equal. In this case, I need to add 2 electrons so that when I subtract 2 for the charge, both sides have a -2 charge. Now my charge is equal on both sides. You will notice that I added electrons to the right-hand side in this reaction, half reaction, to the left-hand side in this half reaction. If I don't end up adding my electrons to opposite sides in my 2 half reactions, I've done something wrong. And so this is a good time to go back and fix any mistakes I might have made. So now we've balanced the electrons' charges. The next step is to balance the electrons gained and lost in both half reactions. These 2 half reactions make up the redox reaction that is taking place in my overall balanced reaction. So what that means is if the left-hand reaction needs the left hand in terms of where I've written it here, if the left-hand half reaction needs 3 electrons, they have to get those 3 electrons from somewhere. They're going to get them from this right-hand half reaction, but this right-hand half reaction is only producing 2 electrons as balanced. And so in order to balance the electrons gained and lost, this is kind of like least common multiple. I need to multiply this right-hand half reaction by 3 so that it'll be losing 6 electrons, and then I'll multiply this left-hand half reaction by 2 so that it'll be gaining 6 electrons. So I'm balancing the electrons gained and lost by my 2 half reactions to make it equal. I'm going to rewrite my 2 half reactions, and I'm going to clean it up a little bit so that I've got some space, but I'll rewrite them with my electrons balanced. All right, you'll notice that I've multiplied through all of my coefficients by 2 for this left-hand reaction and by 3 for my right-hand reaction. I've just written them down here. I like lining up my arrows so that I can see what's going on, because the very next step, step number 7, is to add the reactions together, canceling anything that shows up on both sides of the arrow. When you add chemical reactions together, essentially you add all of the reactants and keep them on the left, you add all of the products and keep them on the right, but anything that shows up on both sides of the arrow identically can be canceled, and your electrons have to cancel at this point. You should have exactly the same number of electrons on both the left and the right, which means you don't write them when you add your reactions together. Another thing you want to keep a lookout for is to see whether or not you've got any waters or H pluses that can be canceled. We don't have any for this reaction, but if we did have H pluses on both sides, we would cancel some. If we had waters on both sides, we would cancel some. So let me rewrite it with these 2 reactions written together. It's a good idea at this point to check and make sure it's still balanced. It needs to be balanced for elements, 2 manganeses, 6 chlorines, all the oxygens have to balance, all the hydrogens have to balance. It also needs to be balanced for charges. The charge on the left should equal the charge on the right. The charge on the right is easy, it's neutral, 0, And if I add up my charge on the left, I've got a +8 for these 8 H pluses. I've got -2 for this guy and -6 for this guy. So I do have a 0 charge on the left. So that's a good double check to do to make sure that I've balanced it correctly. So this is my balanced reaction. It is balanced for an acidic solution. And this is the method of balancing redox reactions. And I probably never would have guessed that just looking at this top reaction by inspection and trying to figure out how to balance it. If you're in basic solution, it works essentially the same way, but we have to add some steps on the end. I'm going to put that in a separate video just to keep it shorter.